Welcome to this special episode of our podcast from the Energy Consortium at IIT Madras. In this series, we will dive into cutting-edge research and innovations that are going to be shaping the future of energy, sustainability, and climate action. The Energy Consortium is a collaborative platform bringing together researchers, industry leaders, and policymakers to address global energy challenges through multidisciplinary solutions. In this episode, you will hear from specialists in energy. So let's get started. Dr. Nishant Modi is a researcher at the ENERG Lab working with Professor Satyanarayanan Seshadri on high-temperature heat pump technologies. His research focuses on developing efficient thermal systems that can contribute to decarbonizing industrial processes.
Hi, Dr. Nishant. Thanks for taking the time out for this. To start off with, could you introduce yourself and tell us a bit about your role at the Energy Consortium and the ENERG Lab?
Hi, I am Nishant Modi, currently working as an R&D scientist at the ENERG Lab within the Applied Mechanics Department at IIT Madras. My research interests mainly include the development of advanced thermal energy systems to improve the energy efficiency of heating and cooling processes. Before joining IIT, I completed my PhD at the University of Tasmania in Australia, where I work on latent heat-based thermal energy storage systems and solar-powered carbon capture systems. That experience really shaped my interest in decarbonization technologies. At the Energy Consortium, I mainly work on process modeling of high-temperature heat pump technologies and identifying the effective decarbonization strategies for industrial heating. One of the key projects that I am leading involves the research and development of thermochemical heat pumps that can deliver efficient high-temperature heat to energy-intensive sectors like dairy, textile, and paper and pulp industries. Since industrial heat accounts for a significant portion of global GHG emissions, I believe innovation in such technologies are crucial to make India a low-carbon economy. Briefly speaking, our goal is to design scalable, cost-effective solutions that can help industries to reduce their dependency on fossil fuels without compromising their operational efficiency.
The fact that you're working on high temperature heat pumps sounds fascinating. Could you explain what exactly they are and why they are such a critical technology in today's energy landscape?
High temperature heat pumps are thermal systems designed to supply heat at temperatures typically above 100 degrees C and in some cases even beyond 150 degrees Celsius. They operate mainly on electricity and can deliver approximately twice as much heat energy as the electrical energy they consume. This technology is especially important because a significant portion of industrial processes, particularly in sectors like chemicals, food processing, and manufacturing, depend on high grade heat. Traditionally, this demand is made by burning fossil fuels in boilers, which contribute significantly to global CO2 emissions. Heat pumps offer a cleaner alternative. They have the potential to replace these conventional systems and can be powered by renewable electricity and can deliver the same amount of thermal output with much greater efficiency and with far lower emissions. So, they are a powerful tool in the broader clean energy transition, especially for decarbonizing industries that have traditionally been hard to abate.
What are some of the major challenges in developing these high temperature systems? Are there any specific breakthroughs or innovations your team is currently focusing on?
There are definitely few challenges in this space. One of the biggest is sourcing components like compressor and sealing accessories such as gasket that can operate reliably and efficiently under the high pressure and temperature conditions. This becomes essentially critical because high temperature heat pumps often use hydrocarbon based refrigerants which are highly flammable and heavier than air. So this makes leak detection and management quite difficult and any leak can quickly lead to a fire hazard. So as operating temperature rise, safety concern also rise with them. Therefore, parallel we are also focusing on alternative heat pump technologies such as thermochemical heat pumps, which use natural refrigerants and eliminate the need of mechanical compression. These systems offer some promising advantages in terms of safety and energy efficiency, but they also bring their own sets of challenges. So we are closely working with our technology partner, that is Trigen Decarbonization Private Limited, a startup incubated from our lab only, to refine simulation models and explore advanced heat integration strategies that can boost system performance. It's a very collaborative efforts involving both fundamental research and practical system engineering.
From an energy perspective, which sectors stand to benefit most from this technology and why?
I believe industrial sectors like chemicals, paper and pulp, textiles, and food and beverages processing, which all require continuous high grade process heat up to approximately 200 degrees Celsius, stand to benefit the most from this technology. Right now, these industries heavily depend on boilers and furnace powered by coal, gas, or oil. In fact, many small factories end up generating steam at much higher temperatures, let's say 180 degrees Celsius, even when they only need 150 degrees C temperature. This leads to a highly inefficiency and energy wastage in the industry. Heat pumps can really be game changer here. First, they enable these industries to electrify their heat demand, which is especially powerful when paired with the renewable sources like solar and wind. Secondly, heat pumps provide much finer control over the steam generation temperature. This allows energy to be used more precisely and efficiently. And third, they come with lower labor and maintenance requirements, which reduce operational complexity and cuts down the operational cost over time. This only does not reduce their carbon footprint, but it can also lead to cost saving in long term as fossil fuel prices become more volatile and carbon regulations will be tightened.
Could you walk us through one or two real world applications or use cases? How exactly does a high temperature heat pump improve efficiency or reduce emissions in that setting?
Sure, a classic example for this is the dairy industry, which needs both cooling and heating for various processes like milk pasteurization, drying, and cleaning. Typically, dairy plants use ammonia based chiller for cooling, which rejects a huge amount of heat into the environment. At the same time, they depend on fossil fuel powered boilers to meet their heating demands. So this is where heat pumps can make a big difference. The heat pump can be designed to capture waste heat from the cooling process and boost it to supply high temperature heat to meet their heating demand in the same plant. That not only boosts overall efficiency but also significantly cuts down their energy consumption and the emissions.
Looks like your work clearly has some strong implications for industrial decarbonization. How do you see this technology scaling in India or globally over the next few years?
I think we are really close to a major turning point. In collaboration with Trigen Decarbonization, our lab has already tested and deployed several steam generating heat pump systems in real industrial settings like sugar mills and textile plants successfully. One of the biggest hurdles for wider adoption in Indian industries is the slightly longer payback period. That's mainly because of heat pumps have higher upfront cost compared to traditional boiler systems, and fossil fuels like firewood and coal are still relatively cheaper in many parts of India. However, the momentum is building. There is a strong policy push towards industrial decarbonization with initiatives like National Green Hydrogen Mission, India's Cooling Action Plan, and National Green Energy Goals. As renewable electricity becomes more widely available and affordable, we believe heat pumps will become an attractive option for industries. Globally, we are already seeing progress. Europe and parts of Asia are piloting large scale high temperature heat pump systems. And I believe that with the right support through incentives, renewable energy policies, knowledge sharing, and strict carbon regulations, countries like India can scale up and adopt these technologies in a big way over the next 5 to 10 years.
Also, beyond your heat pump work, are there any specific projects at ENERG Lab that you're currently involved and would like to highlight?
Yes, absolutely. Beyond the heat pump project, I am also co-leading several R&D projects at the Cooling and Heating Innovation Lab along with Professor Satya. One of these projects I would like to highlight is the development of a simulation tool designed to identify the best high temperature waste heat recovery strategies. We are specifically looking at how to optimally recover the most of the waste heat from solid oxide fuel cell with the goal of supporting combined cooling, heating and power generation, which is often referred to as a tri-generation systems. This helps industry and decision makers understand both the technical feasibility and the cost implications before adopting these systems. On the cooling side, we are working on two exciting innovations. One is the development of advanced low temperature desiccant materials to improve dehumidification efficiency, and the other is a phase change material based milk chiller specifically designed to improve the energy efficiency of milk cooling, something that's special important for rural and small dairy operations. So overall, our lab is looking at the full spectrum from heating to cooling with a strong focus on improving energy efficiency and enabling cleaner, more sustainable technologies.
And finally, for students or young researchers interested in clean energy and industrial sustainability, any suggestions on how to get started or areas they should be closely watching?
First of all, I would say stay curious and build a strong foundation in thermodynamics, heat transfer, and renewable energy systems. These fundamentals are absolutely essential in this field. I also highly recommend getting hands on experience early through research projects, simulation, or internships. Don't wait, don't wait until your coursework is finished, especially if you are a master's or PhD student. Find mentors and collaborators who push you to think beyond lab scale solutions to systems that can really scale. And finally, make sure to communicate your research findings through good conference or journals, as this can really open up valuable opportunities for your future.
Thank you so much, Dr. Nishant.